In the last video I built this power supply. It's based on the Riden RD6006. This is just the power supply controller head. There's no actual power supply included with this. So what I did was to purchase the case, which I got from the same supplier, and I also purchased a 600 watt 60 volt 10 amp switching power supply. So this is a switch mode version of this supply. I will be making a second one of these using a linear supply, so I've got some 500 VA toroidal transformers that I'll be using, but this is the switching version. So it does create some complications when trying to test it because of the noise that the two switching supplies generate. So we've got the switching supply that generates the 60 volts, and then of course we've got the switching controller. I will touch on that briefly as we go through this video, but I'm not really looking at testing the noise on this. You do need specific setups for doing that. In my professional work I do a lot of EMC testing and design to pass EMC requirements, and the test equipment you need is fairly specific. If you look at the various directives and standards that control emissions and susceptibility, you'll see that they do give very specific requirements for the test equipment, and it is for good reason. Otherwise you'll end up chasing faults that aren't actually part of the equipment you're testing. I will give a very quick demonstration of that in a few minutes. But before I get to that, just really a word of caution. As you saw, I put this together in the last video and I switched it on, and I was fairly careful assembling it, and it worked. It came to life, it gave the correct outputs, and I mentioned I was going to pat test it, and somebody asked why I was going to bother doing that. It was a supposed pat tested switching supply I was using, and there wasn't really much else that was in the unit. It's a few wires going from the main socket and switch, and that was it. And if you look at the switching supply, it's got inspected stickers on. Ignore these. This is just somebody that's been trained to put a sticker onto a metal box, and probably doesn't mean anything at all. I doubt it even is put on as a result of inspection. I think it's just part of the assembly process. They slap a sticker on there and that's that. So whenever you do anything like this, you do need to take responsibility for making sure it's safe, and that's it's rarely a case you find something that's dangerous or even not working. But in this case I did. It's one of the few occasions where that sort of testing paid off. Now the supply worked. It gave the right outputs. I was doing some basic testing. It worked under load. However, when I tried to do some ground leakage tests on it, I found that the case, the ground, was sitting at plus 65 volts directly. It wasn't leakage, it was very hard wired to the plus 65 volt out from the switching supply. So if I try to ground this should be a floating supply, which is one of the reasons I use these. I want fully floating supplies, but if I try to ground either of the two terminals, I'd get a huge current flowing, and in theory it should blow the fuse in the supply. So that was kind of confusing at first. I assumed to start with there was a fault in the switching supply. I disconnected the power connector going to the Riden controller, and the short was still there. It wasn't between here, but it was still between the supply and the case, because obviously this wasn't plugged in anymore. So I started looking around, and what I found was maybe not that surprising, but just as I say, a word of caution if you do build one of these. The kit comes with all the screws that you need to assemble it, and that includes these screws that hold the switching supply to the inside of the case. And what I did before I fitted the supply is I used a depth gauge to measure the depth on the supply itself to the whatever was closest to the hole, and then check the length of the screws, and there was about a 2mm clearance, so it seemed that the screws were plenty short enough to not foul on anything. However, it turned out that just by sheer chance, I think, with this particular supply, although you won't be able to see it here, I'll do a close-up under the microscope so you can get a better look. So I'll put that here. and as you can see, there's a lead sticking almost centrally down the hole that this screws into. And although there's a plastic sheet on the underside of the PCB on the switching controller, when I put the screw in, it cut through that, and the screw was basically pressing onto the bottom lead of the component, and the length was such that there was no sign of fouling. It was just long enough to cut through the plastic and create a direct connection. And that pin that you can see through the hole is one of the pins on the output capacitors for the switching supply, and that's the positive output, so it just connected the case directly to that pin. So what I've done is just shorten the screws. I could have put spacers or washers in, but I just wanted to play safe, and this was quite easy to do. So I've shortened the screws, and now obviously the screws don't touch the lead. I've got about a 3mm clearance. That should be fine for what we're doing. I've tried pressing down on the board inside and it doesn't move, so it looks like we've got a fairly good clearance in there. I will turn the plastic sheet around under the supply just to make sure I've got a fresh piece there without the hole in it. But that's one thing to watch out for if you build one of these. Don't assume that the screws are the right length. They didn't seem too long, but obviously they were just that little bit too long, and did cause a problem. Had I not checked that and I'd connected it direct to a piece of equipment I was trying to test, then it most likely would have destroyed the equipment, and so the testing I do is well worthwhile. So what I'll do now is I'll get it connected up and we'll do some basic testing. I'm not going to go overboard with the testing. I just want to see what its basic performance is, what features it has, and how easy it is to use. I still haven't downloaded the manual, so I'm kind of working this out as I go along, and any good design, you shouldn't really need to spend days reading the manual for something like a power supply. I quite like the layout so far. One thing I would say is whoever designed it has done quite a nice job with the way they've done the interface, but obviously comments on that would be welcome. One thing I would say is I prefer it over the Rigol. I think that whoever designed the Rigol supply was having a bit of a laugh with this layout, and although I've had that Rigol now for a couple of years, I still haven't got used to that front panel layout. I think it's a bit stupid. Having numbers in a circle is it's right on an old telephone, but on a digital piece of equipment it's very unintuitive, whereas this supply, the front layout is actually quite intuitive, and so far I haven't needed to try to get the manual to figure out how it works. But I'll go through it. As I say, any comments on that, then please let me know. So as you can see, nice bright display. It's not as big as it actually looks. They've managed to get a lot of information onto a very small display, but it is very readable. So what we have along the top is a status bar. It shows the current time and date. That time and date will be retained if you fit an internal coin cell. So it gives you a real-time clock that's retained through power out. And then on the right hand side you have some icons that show you the various settings for certain parts of the system, and then in the center of that it will show you the current status depending on the mode the supply is in. So for example, if you press shift, you notice that shift appears in that, and it tells you that you're currently in shift state, although there's also an LED on the key itself. The keys that illuminate are nice and bright and very easy to see. I'm directly under some very bright LED lights here, and they're still very easy to see. Bottom left hand corner of the screen you have some more icons that show you the current status of the supply output. So it tells you the current memory you have selected, whether you're in constant voltage or constant current. And then above that you have the current output from the supply, so the voltage, the current and the power. That updates nice and quickly, so once you turn the output on, it updates very quickly. It's again very easy to read, very clear. Again, nice bright illuminated on off button. So they've made a very nice job of getting these keys to work the way you'd expect them to. The beeping gets a bit annoying after a while, but you can turn that off in the menu. We'll look at that in a few minutes. And down the right hand side we have the input voltage to the Riden controller, so that's the output voltage from the internal switching supply. We have the current voltage set point, the current limit set point, and then the over voltage protection and the over current protection. So change the output is extremely easy, very intuitive. So if you want to change the output voltage, just press the VSET button. The button illuminates to tell you that you're currently setting voltage. You can then either just rotate the adjusting knob to set the voltage to whatever you want. You can select the column that you're adjusting. So you can go from volts per click to 10 millivolts per click. It's got quite a nice response. It's not speed responsive. It doesn't make any difference how quickly you turn the knob in terms of the rate at which it changes, but it does have quite a nice response speed. So once you're happy that you've got it set to what you want, just click the button. Here's a clickable knob, so that's quite nice. And exactly the same thing with current. You can set it 1 milliamp at a time, or 10, or 100, or 1 amp at a time, depending on how accurate you want to adjust the current setting. Or you can just type in the value you want. So if you want 2 amps, just hit 2 and enter. If you want to type in the voltage, you can do that. If you want 5.1 volts, just type in what you want. Very quick and easy to use. If you want to use the built-in memory, I believe there are 9 memory slots, then all you need to do is hit the mem key. You get mem showing up on the status bar at the top, and the mem key illuminates. You then press the key that relates to the memory slot you want to save into. So if we want to save into memory slot 8, hit the 8 key. We now have the option to cancel that or save. If we save it, we've now stored that configuration in memory slot 8. If we want to have a different setup, then let's go for 10 volts. And if we want to save this to memory slot 7, then that's all we have to do. To recall a stored memory, just hit the shift key, and then whichever key relates to the memory slot we want to load. It shows you a summary of what we're about to load into the supply, and hit enter, and we now have the configuration that we want. If we want to change to a different one, just select that one instead. So very quick and easy to use. Now, one aspect of this supply I don't particularly like, and I think it's something that really needs to be changed, is if you have the supply turned on, so you have some output from it, and you select a different memory configuration. So let's say we select slot 8. It doesn't turn the output off. So whichever memory slot we select, the output stays on. Now, it could be quite dangerous if you accidentally select the wrong memory and you select 60 volts when you're working on a 5 volt system. Then that could be, of course, quite damaging. It kind of defeats the point of having over voltage and over current protection, because it means that you could very easily, with just 2 key presses, select, as I say, 60 volts for a 5 volt system. So really they should change this. This needs to be off. It should go off whenever you select different memory settings. Other than that, the menu system and the control system seems quite good. If you want to change the overcurrent and over voltage, then again it's just a case of shift, select the one you want to change. In this case we've selected overcurrent, and it adjusts in exactly the same way. You just use the knob or type in the value that you want, and when you're happy you can either press enter or just click the knob, and then if you want to change the over voltage, then it's exactly the same. To access the internal menu, it's just shift menu key. It's quite a nice intuitive menu to use, although some of the terms in here are as a result of I think translation from one language to another, and they're not all particularly meaningful without reading the manual. But once you know what they are, it does make sense, and it is quite a nice menu to use. As I say, you can turn the beeper off if you want to. You can scroll through the various sub-menus. You do have a graphing function. You can pre-configure the memory here as well, and then you have information about the current system, version numbers and serial number. Overall, it's very nice design, nice and easy to use. I would stress again, I don't have any affiliation with the designers, manufacturers of this supply. So far I'm impressed with it. It's exceeded my expectations, and hopefully the testing will continue to prove that it works the way that I want it to. So the setup I have here is an electronic load. This is only a 150 watt load. That's as high as I'll be going on this particular set of tests. I've got an Agilent 34461A. This is currently calibrated, so this is accurate to within a few millivolts. And then we've got the Riden supply itself. I've got the scope hooked up. If you've seen Dave over on EEV blog testing one of these supplies, you'll know that he used a setup like this and he had problems with noise due to what was assumed to be a transmission line caused by this type of lead. And the fact that the transmission line wasn't terminated, this is 75 ohm cable. I've got the scope set to 1 meg input, and of course the output of the supply does not match any of these. The scope's not matched to the cable, but that's not how I'm doing this testing. That's not what I'm testing for. But one word of caution here, before we start doing the testing, I'll power up the supply, and you'll see that even though we've got the supply output turned off, we're getting some significant spikes on the scope. If we zoom into those a little bit, you can see that it's a very significant noise, and the amplitude, or the apparent amplitude of that, is around a volt or a little over a volt. But that doesn't actually exist on the output of the supply. That's not coming down these cables. This is caused by inductive coupling between the switching supply inside the Riden and the various cables and the scope itself. And if you recall, when I put the supply together, I twisted the wires coming out of the switching supply that went into the Riden controller. And usually you twist wires to make the kind of a self-cancelling system within the wire, so each twist tends to counteract any signals picked up in the previous twist. They're out of phase. That's not why I did that. The reason I twisted them together is to reduce the loop area of those two wires. And the reason that loop area is important in a system like this, bear in mind what we've created here is an inductively coupled system. If you look at the signals on the scope, as I move these cables around, it's not because I'm touching it. I can touch it and it doesn't make any difference, but when I change this loop area within this cable, I'll just move this across so you can see it a bit better. So we have this loop area in the cable. That's what's important here. It's because of the way it's coupling to the switching supply inside this unit and the various cables coming out of it. So if I change this, you'll see that it has a huge impact on the scope. And just to clarify that, it's an inductive coupled system. So if I put a ferrite on one of these two cables and you watch the scope, you'll see that it has an enormous impact on what the cable's picking up, because we've changed the way that this system is now working, and we've made what is obviously a very poor system. We're getting a lot of noise and it would make it impossible to measure. If I take this off again, you'll see that that noise, the background noise, pretty much goes away. I'll put it onto the other wire and you'll see that it has almost no impact. That's because this is the active wire. You'd think it'd actually cut out this noise that we're seeing, but when you put it onto the ground then, or the negative lead, which is the one that's coupled directly to the scope, it has far more impact. If I put it on both of these two wires, so they're both now passing through, you'll see it does almost nothing. So it's not cutting out signals going down the cable, it's causing the system to pick up more interference, and you can see it does have an enormous impact. So you do need to bear that or bear that in mind if you're doing this sort of testing. It's not just simply a case of hooking up wires and doing some testing for noise. But as I said, I'm not interested in this noise here. I know what it is, and if you do want to investigate this, then in terms of noise from the Riden supply, then what you can do is pretty much ignore the spikes that you're seeing, and this will become more apparent when we look at the linear version of this that I'm going to do later. If I now turn on the Riden supply, you'll see that what we're getting now is more noise in the what was the quiet spaces between these large spikes, and that's the noise that is being generated by the Riden. If I turn it off again, you can see that disappears, although the large spikes stay where they are because they're the inductively coupled spikes. These small spikes with the Riden on are what is actually being transmitted down the cable. But as I said, I'm not really interested in measuring those in this video. If anyone's interested, let me know. I'll come back and do some more in-depth testing of this, but it does get quite complicated quite quickly when you start trying to investigate this sort of noise, and it's not something I'm particularly interested in. If I want a very low noise supply, I'll use the linear supply. If you're doing testing where you can't tolerate noise on your system, then you should not use a switch controlled supply. It will always cause you problems. Always go to a linear supply if you're doing low noise type work. But this would be fine on a digital system, and this is mainly what I'll be using it for. Okay, so I'll turn that off. I'll just move this lead so I'm getting the scope DC coupled, because I want to look at the DC performance of the supply. So firstly, I noticed that somebody in a comment on Dave's video mentioned the step response of the supply when it was turned on, and I would say yes, there is that. We'll see that in a few minutes. But then the Riden does the same thing. Almost every supply I have does exactly the same thing. You'll get a step when you first power it up, and that's something that you need to bear in mind when you're using these supplies. Is I always disconnect power supplies before I power them up, and if I turn the Riden off at the mains, and we'll get the scope to do a single shot capture, I'll turn it back on, and you see there is a spike when we first turn it on. You'll get that every time. Again, a lot of this is not directly coupled to the output. Some of it is, and you again need to have very specific setup to test for that. But it's not too bad. This is actually not a bad supply at all in terms of spike output when you turn it on. The Riden gives quite a lot of power and quite a lot of voltage out. If you connect LEDs or something to the output and power it up, then you'll see that the LED comes on quite brightly for quite a long time. The Riden does give a spike, but it's much smaller. Okay, so we first turn it on. As you can see, I've got this coupled to an electronic load. I've got it connected to the adjuvants. The way I've got these cables configured is we're measuring the voltage directly at the supply terminals, and then the cables are going through to the electronic load, so we will get some voltage drop in the cables between the supply and the load. So in other words, the load might or will read a little bit lower than the actual voltage coming out of the supply, but the adjuvant should be reading pretty much exactly what's coming out of the supply. There'll be a bit of drop in the terminals, but it'll be very small. So I'll start with 5 volts. We'll see how well that performs. I'll turn the output on. I've got the electronic load set to a constant resistance mode, so it's currently at 20 ohms. I'll turn that on, and we'll turn the supply on, and what we can see is the supply is now on. It's showing us 5.00 volts, about a quarter of an amp, and on the adjuvant we see we're getting 5.005, so far very close. And we're getting on the electronic load, this is also calibrated, we're getting 1.2 watts, which is rounded the same as the supply is showing. Same with the voltage. We're not getting much voltage drop at this low current, so it's fairly close. What I'll start doing now is ramping up the voltage and see how well the supply tracks the correct voltage. So I'll go up a volt at a time. So 6 volts, 7, you can see extremely close, just a few millivolts out. Okay, we'll try entering it through the keys, 25 volts. And here we've reached the current limit that's set to 1 amp, so I'll change that. I'll actually set it to 6 amps so it doesn't interfere with us again, but you can see it's now indicating CC, so it's going to constant current mode. So it does tell you on the display what particular mode it's running in. So I'll change the current limit to 6 amps, and you can see now we've gone up to 25 volts out, and we're still very close to 25 volts on the Agilent. So we'll go up to 35 volts, and again still very close on here. It's shown a bit lower on the electronic load, of course, because we're getting some voltage drop now. We're getting 1.7 amps going through these cables, so there's bound to be a bit of a drop. We'll go up to 40 volts. So looking very promising so far. So we'll now go up to 45 volts. So still only around 10 millivolts out. 50 volts. And we'll go right up to the maximum limit of 60 volts. So we're showing 59.98 on the supply and 60.02 on the Agilent. So very close. We're showing overpower on the electronic load, so I'll change the setting just to allow it to continue to operate. Okay, so we can see that the voltage output is extremely accurate. There's right through the entire range, it's within a few millivolts, and the power shown coming out of it is also very close to the calibrated value that we have on the electronic load. What I'll do now is I'll rearrange the cables and we'll look at the accuracy of the current mode. Okay, so we're set up to measure current. I've got the electronic load set to a constant resistance of 10 ohms, and I'm using the 10 amp range on the Agilent. We've got the supply set to 5 volts. I'll set the current limit to 1 amp and we'll turn it on. So the supply is showing a current of 498 milliamps, 497, and the Agilent is showing 498, so within a milliamp or so. I'll start increasing the voltage and the current will of course start going up, and we'll see if it tracks accurately. So I'll increase the voltage to 10 volts, and we're seeing 990 milliamps on the supply, 991 on the Agilent. We'll get up to 20 volts, and as you can see we are at the current limit, so the current limit is working extremely well on the supply. It's limiting to within a few milliamps of the correct value, so we're showing 1.005 amps on the supply and 1.005 amps on the Agilent. I'll change the current limit, I'll set it down to 0.5 amps, and again we're very accurate, very close to the correct limit. I'll go up to 2 amps, and we haven't quite made 2 amps with the current voltage, so I'll increase the voltage to 25 volts, and now we can see we're getting 2.004 amps on the supply indication and 2.005 on the Agilent. So I'll just keep increasing the voltage. increase the current limit to its maximum of 6.1 amps. Okay, so we're showing overpower on the electronic load, so I'll reduce the resistance on the electronic load. Now have it set to 5 ohms, and I'll start increasing the voltage again, so we'll get up to around 5 amps. So we're showing 5.085 amps on the power supply and 5.09 on the adjuvant. So again, just a few milliamps out. It's very close. I'll keep going up until we reach the current limit on the power supply. We're showing overpower again now on the electronic load, so I'll reduce the resistance value to 4 ohms, and then I'll keep going up on the supply voltage until we hit the current limit. And we're now in, you'll see the constant current limit kick in when we switch from constant voltage to constant current, and that's coming in at 6.097 amps according to the power supply, 6.106 according to the adjuvant. So very close to what it should be. I'm actually quite impressed with this. It's far more accurate than I expected. We can see this is pulling down the voltage from our switching supply input. It's dropped from 65 to 63.9. But it doesn't seem to be affecting the output voltage, so it does look like the 65 volts we set up on that supply is fine. Okay, so we can now do some step responses to the supply output being turned on and off, as well as the response it has for step changes in the load that's applied. Apologies if you're hearing a whining noise in the background, that's the electronic load. Okay, so what I'll do is I'll set the constant resistance on the load to 10 ohms. I'll set the supply voltage to 5 volts, the current limit to 1 amp, and what we can now do is turn the supply on, and we'll see if we get a good response on the output of the supply. And indeed we do. As you can see, it's a nice sharp rise and there's no overshoot, and total time for that rise is about 40 milliseconds, which is quite good. We'll do the reverse, we'll turn it off and see how well it behaves on power down. Again, very good. Nice clean drop, nothing alarming there. Exactly what you want. We'll now go into constant current mode. This is obviously constant voltage. If I turn the supply on, you can see that we're in constant voltage. But what I want to do is use constant current instead. So we can see here we're getting half an amp. So if I change the maximum current output to say 0.4 amps, then we should go into constant current mode. So I'll change that. Let's give it a quick try, and as you can see, we're now in constant current limiting mode. So I'll rearm the scope, turn the supply on, and we can see we have a very nice profile going directly into constant current. Again, I'll try powering off, see how well that works, and again that's fine. Turn the supply back on, put the scope into free run, and what we want to do now is see how it responds to turning the electronic load on and off, which will give it a step response challenge. So we'll turn the load off. You can see that the voltage rises. So what I can do is change the trigger point of the scope, alarm it, and I can now turn the load back on, and you can see that we've captured the step response, and it's extremely good. We'll try and do the reverse. I'll turn the load off, and we've captured the response going the other way. We'll do the same thing now at higher voltages and see if we get the same response. If I go up to 30 volts, Okay, so I've got it set up to go into constant current mode around 30 volts. It'll be a little bit under. Okay, I've armed the scope. I'll turn the supply on, and we can see we're getting a very good response to the supply coming up. I'll turn it off, see how well that behaves. Again, it's looking very good. We'll do the same thing with constant voltage mode. So rearm the scope, turn the supply on. So this is going from 0 to 30 volts. You can see a very nice clean rise, and again we'll capture the fall as well. Again, looking extremely good. So that's a very good response from the supply. It's not looking like it's going to cause any problems. I'll continue doing this testing. If there's any particular test you want me to carry out, then let me know. One final test I'll do here is just to run the unit for a while and see how the internal temperature responds, see if it starts to overheat. I'll run it up to 150 watts, that's only half its maximum power of course, but it will still give us an indication of course as to how thermally efficient this unit is. At the moment the fan hasn't come on, we haven't really stressed it at all, so we'll see at what point the fan cuts in. So I'll remove the scope, we don't need that anymore. We'll turn the supply on, and now we'll just ramp it up until we're getting 150 watts out, which is the maximum that this load can tolerate. So firstly I'll change the constant resistance to make sure we can achieve the maximum power output, and now I'll start to increase the voltage. So that's the maximum power that the electronic load can handle. I will do this again with a 300 watt electronic load just to make sure that the supply can handle its maximum output. And what we're looking at here is the temperature indicated from the internal sensor that's attached to the switching supply. So currently it's saying 27 degrees, not rising very quickly at all, so it is looking very promising. Okay, well it's been running for a while. The fan cut in at about 28 degrees. It's only gone up from 27 degrees internally to 29, and this is at 150 watts continuous load. So it's looking extremely promising. It's not really getting very warm inside at all, so I doubt it's going to have any thermal issues. I will keep testing it at higher and higher powers, but I won't show all the testing, it does get fairly tedious. But as I say, any particular testing you want me to show, then let me know. In the next video I'll just connect it to the software and show you how that works. So far, very impressive supply. As I said, I have no affiliation with the suppliers, I'm not being paid to say any of this. And the only thing I'd say that's negative so far is that the screws that are used to hold the supply in are too long, and that could have been quite dangerous. So just watch out for that if you build one of these. Other than that, so far it's performing extremely well.